Good day everyone. The main objective of this series of lectures is to provide students currently enrolled in digital electronics with some knowledge to assist in their project. The proportional integral derivative controller, or what we call a PID or three-term controller, are the most popular and widely used controllers in industry. So for this project, the students are required to use PID algorithm to control the RPM or the angular speed of a brushed DC motor. Subject to availability, each group will be given either a 6-volt motor or 12-volt motor, each fitted with an encoder. This is the encoder, or the feedback sensor that measures the RPM. At the end of this project, each group should demonstrate a working closed-loop digital control system, where the user can use a computer or PC to enter the desired RPM and the PID parameters, which are the Ki, the integral part, the Kd, and the proportional part. Now these information, which are the RPM and the PID parameters, will be straight away directly fed to the Arduino. However, for simplicity, we could imagine that the following closed loop system look like this. So this is our encoder here, which is measuring the existing status. We have some sort of a summing junction where the desired RPM, as if it is coming from a computer, and the existing RPM is from the encoder. Now the difference is our error, and based on the PID parameters and the error, we can actually calculate the desired pulse width modulated output signal. Now the pulse width modulation, or PWM, is a technique for getting analog results with digital means. So it's basically a square wave signal which is switched between on and off. And this on-off pattern can simulate voltages between 5 volts and 0 volts. Now this can be achieved on a scale of 255 using Arduino to a scale of 0. This can be achieved using a cold to analog write. So analog write of 255 will give you a continuous 5-volt output. If you write analog write with 0 between the parentheses, you will get a 0% duty cycle. If you would like to achieve a 50% duty cycle, that means half the time of the pulse is on and half of the time the pulse is off, you have to use analog write 127, which is the midway between 255 and 0. Now, since most DC motors, they run on higher than 5 volts, we have to use some sort of a H-bridge, which allows the 5-volt PWM coming from Arduino to actually control a transistors that allow a higher voltage and higher current to arrive at the DC motor. Also, the H-bridge main task as well to allow for forward and backward rotations of the DC motor. The reason why we can pull out more current or voltage from H-bridge is because the H-bridge has its own power supply. And the power supply should have the right capability in terms of voltage and current. Please always read the datasheet for the H-bridge and your DC motor, because H-bridges are different, and each motor has a suitable H bridge for it. Now, even if your DC motor is a 5-volt only motor, you should never run it directly from Arduino, because each pin in Arduino can provide or sync up to maximum of 40 milliamps, but the recommended current is 20 milliamps. Also remember, in the PID algorithm, you should have the difference equation somewhere here. That calculates the right PWM output, which is based on the error. Next, we will be discussing the mathematical model for the DC motor. Without the model, we won't be able to actually achieve our objectives.